Hello everyone and welcome back to my channel. Well, it's been a little while. So in this video I'm going to talk a little bit about enhancements that I've added to my ultrasound listener project. Namely, and I think some of you will recognize what's on the breadboard here, there is an Arduino Nano. And I have a two-line LCD display that right now is showing the frequency count of my local oscillator, the VN bridge oscillator, that I introduced maybe a little while ago. Might have been video 4, I don't remember exactly. But it is important. Let's see if we can zoom in on the display. It isn't important to be able to see what frequency you're tuned into once you're out in the field. A little bit of glare there. Listening to whatever critters like bats that you may want to know what frequencies that they're chatting about at. Okay, I can see that now. So obviously I can't take an oscilloscope out into the field, but this LCD two-line display will be perfect. So it interfaces to the Arduino, and I'm just going to talk a little bit about some of these features before I get into the details of the actual sketch that I found. I found it mostly on the internet, YouTube, other people's sketches for interfacing the LCD display, and there's a couple other features I'm going to get into insofar as tuning the local oscillator. We're going to get into digital potentiometers instead of the mechanical potentiometer that I use right now, right here. There it is. And we'll see how well we can do with those, or how badly we can do with those. Well, I think they're going to be better than using a mechanical one. But let's change the frequency on the mechanical through the mechanical potentiometer and see what the range is. Right now it's at the upper end of the range, 118 kilohertz. Floats around. As I bring my finger near the potentiometer, the actual frequency changes. One thing also that I'm going to maybe not get into too much detail, but I'll give everyone a reference, is the frequency counter sketch that I also got from someone else's YouTube channel that makes this frequency display possible through the Arduino. So nothing here that I've actually invented on my own, but rather I'm just using what I found other people to be using. Okay, let's see if we can tune this. So as we change the oscillator frequency, I'm going to tune it down. For unit turn of potentiometer, at the beginning, at the high end of the frequency, doesn't change a lot, and as we drop down toward the low end, it changes more dramatically per unit of turn. So 9,600 hertz all the way to 100,000 plus hertz. Excuse me. So that should give us a wide range of local oscillator frequencies in which to, tune in a bat or what a little dormouse that we might be listening to. So that is how you do it with the mechanical potentiometer, and now we're going to get into see how well we can do with some digital potentiometers. The mechanical potentiometer it's a 100K potentiometer, and as a first attempt I'm going to replace the mechanical potentiometer with an equivalent 100K, two of them, because this is a dual gang potentiometer I'm using. I'm going to replace it with exactly two digital potentiometers of 100K. So I'm going to connect their wiper terminals and the B terminal together, the A terminal connected to the R1, A terminal to C2, go to a timing capacitor, and wiper and B1 terminal to the R4 resistor. So in case you don't recognize this is the schematic of the Wayne Bridge oscillator. This resistor, I think I incorrectly labeled it 5.6K in the introductory video, but actually it works with 7.5K. So that's about it. The output of the oscillator goes to a transistor signal conditioner, where it's connected to a 5 volt power supply, like the Arduino is powered by 5 volts, and squares up the sine wave output, and it's fed into one of the pins of the Arduino, where it is frequency counted, and it's digital pin 5. That's what I have. Okay, so let's pause for a minute and let's substitute in the digital pots. Okay, I've wired up the digital potentiometers. They are AD5220, which they're single potentiometers. They are located in the circuit there and there. So the way we tune these will be through something called the rotary encoder right here, which also is wired into the Arduino, and it requires its own sketch. And I'll show you the sketches afterwards, but first of all, let's see how this thing is working. One thing about the digital potentiometers is these AD5220s are rated for 5 volt operation, and the oscillator up here used to be around a TL071 op amp, which does not work very well at 5 volts. So the op amp that I substituted is a TLV 2770 low voltage rail-to-rail op amp. It's pin for pin compatible with a TL071, but it'll work at 5 volts. Actually, I think these digital potentiometers don't have any trouble working in this particular circuit, even if the oscillator is powered above 5 volts. But for the time being, I have two power supplies to power the oscillator. This is something else for the moment. We don't need to discuss it. But anyways, one power supply powers the oscillator. Another power supply powers the Arduino at its V input pin, which I provide about 7 volts, and it takes it down. It has its own 5 volt output pin, which is this wire here, and it powers the rest of the 5 volt equipment around here. Incidentally, the when these digital potentiometers are used in circuit, the none of the terminals themselves are supposed to exceed 5 volts, which well, I don't think they do, but in any case, to be safe, use the low voltage op amp that you can power with 5 volts instead of 12 volts. So let's power it up and let's see what we get. I'll apply power to the Arduino first, and here we go. There's a classic greeting hello world that I programmed, and now we'll power up the oscillator. It's not oscillating as they're showing 0 frequency. There we go, it's back. 7755 hertz, 7.7 kilohertz. So let's see now. One thing I'll note, I'm looking at the oscilloscope, is the peak-to-peak voltage has dropped. It used to be around 3 volts, and I'm getting 1.68 volts. So there is some explanation to that, but before I get into it, let's see what we get as we try to tune incrementally, have the tune the potentiometers up in, actually they're at their full scale resistance right now. That's why we're getting the low frequency. So we'll increment them down, increment the wipers down toward the B2 terminals, B1 and B2 terminals, right there, and see how the frequency changes. Okay, so here we go. We're gonna give the rotary encoder a twist. Okay, so 7.7. Maybe I'm going the wrong way. Yeah, I'm going the wrong way, so it's not moving. Okay, here we go. 7811. How much was it before? 7756. 7811. So let's just make a note of that incremental change. So 7810, and the previous was 7756. Yeah. All right, and we'll keep going. So per incremental pulse of the rotary encoder, I'm getting something like 55 hertz change in frequency. So let's keep going. This is I think this is a 12 turn, 12 clicks per turn rotary encoder. And let's keep going, trying to make this go up all the way. (9,000 hertz). Well, let's see if we could make it go all the way to 100,000 hertz. But as you can see, every click, 10872, 10983, advances it less than 100 hertz. And as we keep going higher and higher in frequency, we started off with about 55 hertz frequency change per click, and okay, 14,320, 14,513. So we're getting close to 100 hertz frequency change per click, and there's a reason why this is not constant per every click, and that the reason is that the frequency is dependent upon 1 over RC time constant. So what I'm changing linearly is the resistance value of the digital potentiometer, not the so the time constant changes linearly, but since frequency is 1 over RC, frequency will not change linearly. So we're at 25 kilohertz, 26, 27,535, 28 to, yeah, so we're getting 1.4, what was it, 25, about 700 hertz now per click. Yeah, close to it. Let's keep going, keep going, keep going. And incidentally, the output still is fairly constant. It's dropping actually. And I've actually lost it. Frequency count is 0. So let's see if I can get back a few clicks. Will it come back to life? Ah, it's back. So around 30 kilohertz, it begins to waver. Gone, 0. And the reason is the peak-to-peak output voltage swing has dropped to such an extent that the little signal conditioner transistor circuit that I have doesn't amplify it enough. But, well, things work fine when it comes to the mechanical potentiometer, so what's going on with the digital potentiometer? Well, without getting into too many details, if you look up the data sheet for just about any digital potentiometer, including this AD5220, the data sheet will spec that there exist capacitances at all the terminals, including the wiper terminals, to ground on the order of around 40 or 50 picofarads. So I'm using timing capacitors right now, C1, C2, around 180 picofarads. And if I'm adding another 40 or 50 picofarads shunt capacitances to ground, it's a significant amount of capacitance to add in this feedback loop of the oscillator. So the feedback loop is actually being modified significantly by the substitution of mechanical potentiometers with digital potentiometers. So what's the way around that? Well, the way around that would be to increase C1 and C2, let's say 10 times. And instead of using a 100K digital pot, use a 10K digital pot. So that way any insertion capacitance, 40 picofarads in relation to 1,800 picofarads, will be small. So I do have a couple of digital potentiometers that I've ordered that are 10K. Different variety from the AD5220. The AD5220 is what you call an up-down incremental digital potentiometer. The ones I've ordered are, I think they're I2C or SPI type devices, which means they're just used a little bit differently, a slightly different sketch, programming sketch for the Arduino. And I'm going to pause, wire those in, and reprogram the Arduino for their use and see what we get in that respect. So stand by. So I'm showing the oscilloscope display. You have the yellow trace, which is the output of the oscillator offset by some bias voltage, and the purple trace is the output of a transistor signal conditioner I have input as an input to the Arduino frequency counter pin. So the Arduino triggers on the falling edge of the purple trace. So let's see what happens to these waveforms as I increment the rotary encoder to decrease the potentiometer resistance, and at some point I get a dropout. Well, I think that dropout can probably be fixed to some degree or another, but by rebiasing the transistor. But right off the bat, I would say the output of the oscillator is only 1.5 volts peak to peak with the insertion of the digital potentiometers, whereas before with the mechanical one it was close to 3. So let's see what happens as I tune it up, starting from around 7,500 hertz. Keep going up. Over 10 kilohertz. I think we had get a dropout around 27K. Let's speed up the scope a little bit. My cat is here, by the way, keeping me company. Yeah, the output amplitude is beginning to, I think, drop a little bit. It's 1.4 volts now, peak to peak, 1.32, and see, there lies the problem. The yellow amplitude is dropped to such an extent that the falling edge on the purple waveform is disappearing. So it's not triggering at this point anymore. Actually, even prior to that. Yeah, this is sort of like the that's the edge of it right there. Triggering, the Arduino drops out at this point. Okay, so let's see what we can do with 10K digital pots and 1800 picofarad timing capacitors. Okay, I have a dual digital potentiometer configured now, an MCP 4241. It has 2 internal digital pots. The other ones that I were using were AD5220. They're still here and there, but they're not connected. So made some slight modifications to the Wayne Bridge oscillator. I notice I have to fiddle with this resistor here to set the voltage output between 2.5 to 3 volts. So sometimes 7.5K is a little bit too high, it's clipping and distorting. 5.6K is a little bit too low, depending on which digital pot I'm using. So another thing I'll point out is the fact that these digital pots have a maximum current rating that can be pulled through the wiper terminal. And for this one, the MCP 4241, it happens to be 2.5 milliamps. So the that 2.5 milliamps will be restricted or limited by the value of R4 and R1. respectively on each branch of the digital potentiometer. So if I have an output voltage that is swinging 2.5 volts each way, that's a little bit too much, I think. Let's just say it's peak to peak, it's 3 volts, 1.5 volts peak. And so the conservative approach is to take the wiper all the way to the A pin. That will basically bypass the internal resistor and maximize the current draw through resistor R4. So let's say, for the sake of argument, that this branch here is ground with respect to AC. So 2.5 volts output will appear almost entirely across this resistor. So the calculation for the current, it's right here. So I get half of the 2.5 volts peak divided by 2.5 milliamp, which is the data sheet says that you can put through that wiper, gives you a minimum value of 500 ohms for that resistor, R4 and R1, which right now I have 1500 ohms, but with comfort I can go back down to 750 ohms, which was what I was using before. Now, this resistor also sets the highest frequency of oscillation as well. So in order to get my range, upper range of almost 100 kilohertz, I have to take it back down eventually to 750 ohms. But anyways, I'm up to the capacitors. I bumped them up to 1800 picofarads instead of 180 picofarads because I'm using 10K digital pots instead of 100K. So I upped the capacitance by tenfold to give me the same time constant. And it'll be more immune to the parasitic capacitances that are in the data sheets from each of the branches, pins of the digital pots with respect to ground. So they appear. Okay, so now I'll demonstrate the operation as far as tuning this circuit through the Arduino and a rotary encoder that I have here. I'll maybe get into the details a little bit later, but the rotary encoder incidentally has some resistors and capacitors around it that form a, let's see if I can get this in clearer view. Form a little bit of a hardware debounce circuit. So if I twist this a little bit too fast, I might get some spurious output on the output pins. And basically these resistors and capacitors are just low pass filters. I take the outputs across the capacitors to the input pins of the Arduino, and I'm actually using one of the interrupt pins of the Arduino to basically process the rotary encoder input. Well, I'll get into that a little bit later when I show you the sketch, but I'm not going to go into it too much. I'm sure you can probably all look up the sketches done by other people. Let's see if we can see the frequency. Oh, there we go. Okay. That's about, if I keep my finger on it, you can see it's 7,762 hertz. Okay, yeah, this is another useful little gadget to have, is this I2C liquid crystal display, which is also very easy to interface to the Arduino. And the frequency counter is a sketch that I also found on YouTube. So let's see what we can tune this to. Okay, so starting, yeah, I don't want to block the view. So starting at 7,763 hertz. See if we go up on the frequency. There we go, one notch. And now we're to 7806. So I'm just going to write that down. One notch at the lower end goes up to 7806 from 7762. This is a 128 step digital pot as we bring it up all the way to the upper end of the frequency range. See how it changes. So right now it changed maybe by 40 something hertz. Let's just keep going. All 128 clicks. This is a non-volatile digital potentiometer, whereas my previous ones were volatile. So what I do is every click I update the memory registers, non-volatile memory registers. I read the volatile memory registers and write them in to the non-volatile memory registers. So I'll have retention of the resistance value of the wiper and the set frequency when I power it off and on the next time. So let's just keep going. It takes a lot of clicks to get up to the upper range, especially if the changes in frequency at the lower end are so little to begin with, which kind of makes you wonder whether or not, you know, this technique for tuning the local oscillator is actually practical. Well, it is practical from the point of view that if you look at a few previous videos where I mentioned I had the whiteboard block diagram on display, and I mentioned that it's kind of nice to have the local oscillator frequency set to less than the lowest frequency of your input signal. And the reason for that was to avoid a phenomena called spectral inversion. Well, with digital potentiometers, it's possible to have a filter, an active filter, let's say two module second order Salient key high pass filter that can track the local oscillator, because the filter also can use digital potentiometers to tune its cutoff frequency, and it can be exactly the same frequency as the set to the same frequency as the oscillator frequency. I might need to use like a quad potentiometer, because these potentiometers, although the internal pots themselves are matched very well, the actual tolerance between chip to chip tolerance can be as much as 20%, according to the data sheets. Anyways, here we are. We're at 47.3 kilohertz, and just to check our calculated frequencies. Okay, here's an earlier measurement, 45.9 kilohertz, and the calculation was 54.75 kilohertz. So this is a difference minus 16% on the high end. And if take into account the fact that the digital pots can vary by as much as 20% from the published value. The 16% is actually within that specification. It's not bad. Now, at the other end of the scale, we have 7,751 hertz as the measured value, and the calculated value was 7619. That is a 1.7% difference, higher 1.7%. And the reason being is that the low end, well, yeah, the low end, that doesn't make sense, does it? The low end should see the full resistance of R4 and R3. Low frequency corresponds to high resistance. So I was thinking, yeah, these figures should be the other way around. The R4 is a resistor that is that has 5% tolerance, and the digital pots are 20% tolerance, but I'm actually getting the opposite. Higher error on the high frequency, which corresponds to the digital pot wiper going all the way up to A, in other words bypassing the resistor network in the digital pot. So that's a little bit unexpected, that I would get high error on the upper end of the frequency. The upper end of the frequency corresponds to, yeah, the low end corresponds to the wiper going down to the B terminal. In other words, the full digital pot is in circuit with R4. Okay, but it is what it is. So 47,329 is the high end, and the previous value was 45,612. So that's a, oh, how much is it? 1,700 hertz frequency jump. Yeah, yeah, it's about that, round it off. Whereas on the low end of the scale, it's more like 44 hertz frequency jump, and that's primarily due to the non-linearity of this equation, frequency inversely proportional to the resistance. But in any case, let's power this off and let's see if the system, you might have just seen my cat, if the system remembers the frequency where it left off. Let's just detune it away from the high end. We don't know what the default setting is. Okay. Oh, I have to entertain my cat here for a little while. Okay, so starting at, let it set to 30.7 kilohertz, and just do a quick power off, and we'll power it back on and see if it remembers. Ah, yes. Hello world. What a nice way to start the day, huh? Okay, 30.7 kilohertz. Yeah, there it is. It's the same. Okay. Okay, I might show you the sketch that I have right now. Sort of, this gives you an idea how useful these digital pots will be, and including the Arduino and liquid crystal display in whenever I have this all into a chassis and take it out into the field to tune into frequencies that ultrasound frequencies that I want to listen to. So, okay, let's go to the sketches. So let's have a look at the Arduino Sketch that I'm using for these three I/O devices, namely the rotary encoder, the 2-line 16-character liquid crystal display, and the digital potentiometer, the MCP4241. So it turns out my screen recording software does not work well with the Arduino IDE. It starts and stops as I scroll the screen, so I've did a series of screen captures, and I've actually even zoomed in a bit on the photos viewer, so you can probably see the script a little bit better than had I just did a straight screenshot. So to start off with, I have some variables that are attached to pins 2 and 4 for the A output and B output of the rotary encoder. Pulse pin and up-down pin, these were used with the digital pot, the AD5220 in the just a little bit earlier in the video, but they're not important anymore. I just left them in there. Chip select pin 10, which is the enable disable MCP4241. I declare some 8-bit commands and assign them to integer variables, 16-bit integer variables. Probably don't need the static keyword, but doesn't matter. So these are commands that are sent to the digital pot to read the volatile registers, write to the volatile registers, read the non-volatile registers, write to the non-volatile registers, and even a couple to read and write to the internal EPROMs. Although I didn't use these in the end because I think there's a limited number of times you can do a write to an EPROM anyways. And these are essentially just from the manufacturer's memory map for the device. Basically the device is data sent to the device in the form of 2 8-bit commands, a command and a data byte. So if you're writing to a memory address, it will contain an 8-bit command and an 8-bit data byte. So let's quickly look at the manufacturer's data sheet, and here they are. So the commands are the first 8 bits of these words, and in some cases write data, read data even contains, well, two data bits, but they're really unused, they're zeros. And what was in my declaration of variables is basically just out of this table here. So going back to, okay, so I declare a few more variables down here. Pulse counter, which was also used in the AD5220, but it's not really used at the moment. Maybe it is, but it's not that important. And a few also integer variables that are used to store the wiper settings upon read from the registers, and then verifications for checking to see if it was written into the non-volatile locations. I use other variables for that. So let's move along into the next screenshot. So this is the next screenshot right after the read and write commands. So not getting into these ones so too much. There are a few variables that are declared, which is part of the internal timers of the Arduino that actually do the counting of the external clock pulses. So we'll get to that a little bit later. We sort of start off with declaring a liquid crystal object, liquid crystal display object at I squared C location 0x hex 27. That's a 16 by 2 display. And then we get into the setup routine where I declare the A pin and the B pin as inputs from the rotary encoder. So it has two outputs, an A and a B, that differ in phase. And you determine the direction of the rotary encoder, which way it's being turned, by looking at the B pin output in relation to the A pin pulse. So chip select pin is set as an output, and immediately it's set high to disable the digital pot, and I attach an interrupt to a subroutine called increment, and that interrupt is one of the user interrupts interrupt pins on the Arduino, where I have the A pin of the rotary encoder connected. So continuing on with the setup function, I initialize the serial monitor, I initialize the LCD, turn on the LCD backlight, and set the cursor to 3.0 and print the friendly hello world for 3 seconds. And then I call a function called setPots. And now we'll see what I do with the potentiometers in that function. So this is setPots right here. So what I do is I read the non-volatile, both the two non-volatile wiper registers. So the data, this is a subroutine that I've written up. I'll show you later. It takes two 8-bit words, a command and an 8-bit data word. In the case this is a read command, there is no data to be written, and I store the result that comes back in variable wiper 0. Here with this bitwise AND operation, I zero out the first 8 bits of the 16 bits of wiper 0 because they're not data, they're they're status bits with and there's an error bit set there if you didn't do something right. You know, in the debug stage of this program, I did have a look at those bits to make sure that everything was working right. So I do the same thing for wiper 1 and set the first 8 bits to 0. And here, this is a little bit of error correction that I've devised. In case the two wiper values go out of sync during the operation, they're not supposed to, but it can happen through spurious noise. If they go out of sync and obtain different values during the last time the unit was powered on, I read those values in, and I divide and average the two out. So right shift by 1 bit on each one is equivalent to a binary divide by 2. And then wiper 0 contains an average of wiper 0 and wiper 1. And I assign that same average back to wiper 1, and I write the two values to the volatile memory registers of the pots, and they're ready to go for this power up sequence. This set pots is executed upon power up. Do a little bit of a delay, and I print out on the serial monitor the values that came back from storage in the non-volatile memory locations. Okay, let's move on to the next screenshot. Okay, let's have a look at the interrupt routine that processes the rotary encoder pulse. So once the A pin from the rotary encoder goes low on the falling edge trigger, the program goes into this routine where it finds out the last time it was in the subroutine by keeping track of the interrupt time. And if it's greater than 5 milliseconds, incidentally, most of this rotary encoder processing routine I got also from a YouTube video by Ralph S. Bacon. I'll provide some links at the end of my video where you can go watch his stuff as well. So, and this is basically, it's deep bounce filtering with the argument that if there is any noise on the rotary encoder outputs, it happens, a few bounces will happen within 5 milliseconds or less. So if the interrupt time interval is greater than 5 milliseconds, it processes everything that's in increment, otherwise it exits. So the first thing, the pulse counter, it's not really used, but it's left over from the AD5220, are the commands that are going to be written to the pots are set. Either they're increment commands or they're decrement commands, just 8-bit commands, depending on which way the rotary encoder is going, and that's determined by the status of the B pin. It's either high or low when the A pin falls from high or low does a from high to low transition. So that is an indicator of the direction in which it's being turned, the status of the B pin. So I call SPI begin, and you'll also notice I even experimented with SPI begin transaction, where I set the SPI settings, but I didn't have consistent success with this for some reason. But SPI begin seems to work. I set digital write the chip select pin low to enable the digital pot, and I transfer command 0, and down here I transfer command 1. So the digital pot knows that the commands are addressed to either number 0 or number 1, and that's determined by the first 4 bits of the command word. So that's the 4 bits contain the address, unique address to each digital pot. And the address of the non-volatile ones will be different from these. So these are address 0, address 1, 0 and 1, and non-volatile ones will be 2 and 3 in binary. So once this 8-bit transaction is over, I call SPI end, and I move on to the next part of this increment. So continuing on with the increment function, I read the volatile memory registers of the first pot, down here of the second pot, and I assign it to wiper 0 and wiper 1 variable. These lines zero out the first 8 bits as they're not to data, so I'm just left with the right hand side of this 16-bit number, that is the 8 bits of data. I do insert a little bit of delay in between these write functions, I'll explain the details working of right pot in a minute or so. And I also chose to yes, this is the these are the commands where I'm storing the red values from the volatile registers into the non-volatile registers. And this was like a monitoring variable where I was checking to see what the status of the operation that was coming back for any errors. And these operations are to read what was stored into the non-volatile memory registers to make sure that in fact what is read back is the same as what was initially read from the volatile locations. So this is a little bit of a debugging I was doing. And down here I go into the serial print monitor where I was actually printing out the values that were read for a visual check. So this is the remainder of the increment function. So it ends and re-enables the interrupts because I disable the interrupts at the beginning of the routine because you don't want other interrupts to interrupt a interrupt service routine. So here's the write pot function. So write pot takes in two 16-bit data words, command and data format. And first of all, start off with disabling the interrupts while the SPI transfers are taking place. Again, I was experimenting with SPI begin transaction, but did not have consistent success with it. So SPI begin was the one that actually works very well. So what I do here is I use SPI transfer 16 because this is a 16-bit transfer instead of the 8-bit where I was just reading from the non-volatile pot memory locations. So I do a little bit of binary operations on the command and data where I shift the command bits, command data over 8 bits to the left. So what that does is basically it leaves a pad of 8 zeros to the right hand side because the command is supposed to be in position of the first byte of data, and the data through the binary AND operator I zero out the first 8 bits through the binary AND operator, and this is basically a hexadecimal number 00FF that represents four binary zeros, 4 binary zeros, 4 binary ones, and 4 binary ones. And then the two are bitwise ORed together into an aggregate 16-bit word where the first 8 bits of command are in the first byte and the last 8 bits are the data byte in one 16-bit word, and it's transferred out to the SPI device through SPI.transfer16. And the output result, returned result, is stored in this RET data variable, and sometimes it can be just a status byte, or it can or 2 bytes, or it can be information that you're actually looking for. So after we're done, we return the CS pin back to high to disable the SPI bus, call the SPI end, and re-enable the interrupts. Okay, so let's have a look at the timer function that actually counts the pulses from the local frequency oscillator. So I'm not going to spend too much time describing these three internal interrupt handlers, because all full credit is given to Anas Kuzecki, and here are a couple of YouTube videos that I basically followed to. I mean, it's a copy what I have of his work, and it works just fine. It uses hardware level timers to count the pulses coming in on a data pin on the Arduino, and all of this is it's all set at the hardware level, and you don't have to even declare set the pin that the pulses are coming in on. Yeah, it's all the hardware level. So yeah, I don't have too much to say about it other than yeah, follow. If you want to use the same tool in your own work, follow his video, and it works on the Nano to use the Nano as a frequency counter. So this is the loop function. It doesn't do much because just about everything is handled through interrupts. Start count 1000, that is a call to the timer subroutine to count the pulses coming in through the local oscillator. And all this structure here, while not next count, that's all attributed to Anas Kuzecki. Basically got it from his video. So basically printing to the LCD screen the frequency, echoing the same result to the serial monitor, just formatting, erasing the previous result by writing blanks, and you know, each time it loops, it does this. It prints the total counts, likewise to the serial monitor, and that's about it. Keeps going and going. I hope that's been descriptive enough.